Hi, this is Paul, ready to get started with the first script for Module 1, Week 2. I'm assuming that you have looked through the first page of the executive summary, or better yet, that you've already watched Kate's preview video on those topics. What we're going to do today is introduce concepts of length and angle into our study of vectors. And let's begin with length. I'll set up the screen, but I think this time I'll explain how I'm doing it. The first line sets up the basic screen parameters, and mar equals C1111 means I want the narrowest possible margin, just 1 unit on each side. PCH equals 20 means that if I plot points, they'll show up as solid dots rather than hollow dots. Saving this as a variable named pars would provide me with the opportunity to reset the original parameters, but in fact I'm not going to do that. The plot line lets me specify the extent in the x direction and the y direction. Since I don't need to label the axes, I've set xlab and ylab equal to the null string, and importantly, ASP equals 1 means 1 unit horizontally equals 1 unit vertically, because we're doing honest-to-goodness Euclidean geometry today. I set axes equal to false because I want to set them myself. And the choice 1 and 2 gives me axes at the left side of the screen and at the bottom of the screen, which is the normal thing to do for this type of display. Now let's set up a vector. 4 units east, 3 units north, and plot it. And when you plot it, you can visualize the length of the vector, which in fact is 5 units, and its direction, which is a bit less than 45 degrees above the horizontal axis. You all know how to get the length. Use the Pythagorean theorem. Take the square root of the sum of the squares of the components. You get 5. But in R, it's even simpler. If I say v squared, R will square each component of the vector. And if I ask for the sum of v squared, I'll get 25. Taking the square root gives me 5. And now I have a solution that works for vectors of any length. Here's a vector in R7, and I can calculate its Euclidean length of 6 by the same technique. It's useful to have a function that does the job, so I will define a function that takes the square root of the sum of the squares and call it norm with a capital N. I use a capital N because there's already a function in R which is norm with a little n that does something quite different. Now let's extend the concept from length to the dot product of two vectors. Here are my two vectors, which I'm showing in black. The first one has an x component of 3, a y component of 1. The second is 2 minus 1. And the way you calculate the dot product is multiply the first components together, multiply the second components together, take the sum of the two products. But of course, R is happy to do that automatically if you just ask for v1 times v2. It multiplies them component by component, and sum adds them up. So we have a way of doing the dot product for vectors of arbitrary length. Let's define a function to do this. %.% seems the most natural choice, and it's just the sum of x times y. I can use that function with the quotation marks around it as if it were a function like f, and it gives me the answer 5. But what I really like to do is put it as an operator in between the two vectors. So now we've got an honest-to-goodness dot product. And in terms of the dot product, of course, the length is just the square root of the vector dot product with itself. Now we can introduce angle. The way we introduce angle is by taking advantage of the fact that there's an arc cosine function available on any self-respecting scientific calculator that can be defined in terms of infinite series. And I'm going to define the angle between two vectors to be the arc cosine of the dot product of the two vectors divided by the product of their lengths. What do I get? 0.785, etc. That's not in degrees, that's in radians. If I want to convert it into radians, I have to multiply by 180 degrees divided by pi. But let's do this once and for all by defining an arc cosine function spelled with a capital A that gives the answer in degrees. And now the answer that we get from our two vectors is 45 degrees. And sure enough, if you look at it, the angle between the two vectors looks like half a right angle. Notice, by the way, that if I stretch or shrink the diagram, it always readjusts itself so that a unit along the x direction is a unit along the y direction. So no matter how I resize this window, the angle between those two vectors is going to be precisely 45 degrees. That's the effect of setting an aspect ratio of 1. Now we might as well write a function to do this. Angle between calculates the arc cosine of the dot product over the product of the lengths. And now in one fell swoop I get the angle between those two vectors. Let's think briefly about components. It's a good idea to reset the plot because these vectors are going to be slightly longer than the others. I'll introduce two standard basis vectors and give them names E1.2 and E2.2. The dot 2 means that they're two-component standard basis vectors. I can plot them and display them in green. If I take their dot product, of course, I get 0. That's an indication that they're perpendicular or orthogonal. Now let's display our vector v again and calculate the angle between the vector v and the first standard basis vector. The answer I get is a little bit less than 37 degrees, and this actually displays correctly. That is, if you measured it with a protractor, you'd read 37 degrees. By using both standard basis vectors, I can extract both components of the vector v. They are 4 and 3 respectively. So in general, the dot product is a good way to extract the components of a vector relative to two mutually perpendicular axes. I can make any vector I like, of course, by taking a linear combination of the standard basis vectors. If I want a vector whose components are 12 and 5, I just multiply 12 by the standard basis vector that's got a 1 in the top position, add on 5 times the standard basis vector that has a 1 in the bottom position, and I get a vector whose components are 12 and 5. I can plot that on the screen equally well. Or I can start with length and angle and just evaluate the sine and cosine of my angle in order to get the two components. Notice in this case, if I use the built-in cosine and sine functions, I have to convert my angles from degrees to radians. But I'm going to fix that in our little Math 23 library by defining cosine and sine functions with capital C and capital S that accept angles in degrees instead of in radians. So there's my third vector plotted. And now that we see how to do this, let's do it once and for all. Write a function called make2dvec that takes the length and the angle, computes the components, and makes a vector in R. There's the definition of the function. And when I say to make a two-dimensional vector with a length of 17 and an angle of 28 degrees above the axis, I get the same vector that I had already constructed. Sometimes you want to resolve a vector in the plane into two components, one along the direction of a certain unit vector and another perpendicular to it. Let's clear the plot. Pick a vector A anything will do. I picked first component of 2, second component of 1, and then I make it into a unit vector by dividing by its own lengths. You can see that vector has a length equal to 1 and is just specifying a direction. Now let's pick a vector v and plot it. Any choice will do. This is a perfectly good one. And now what I'm going to do is take the dot product of v with that unit vector. That gives me the component along that unit vector. Multiplying by the unit vector itself will give me back a vector. And when I display that in green, you see that I now have a vector in the same direction as the unit vector. That's the component of my red vector along the unit vector. What makes it special? Well, let's look at the other component. The other component, which I'll call v2, is the result of subtracting the vector v1 from the original vector v. I'm going to plot v2, but I'm going to plot it with its tail at the head of the green vector. That is, I'm going to plot it from v1 to v. And when you look, you'll see the two green vectors are at right angles to one another. So I've resolved this vector into two mutually perpendicular components. Resolving a vector into perpendicular components relative to specified axes is a very standard operation when you're doing physics with vectors. I'll show you again. If I stretch or shrink the screen, that right angle remains a right angle. That's because the aspect ratio is 1. Everyone knows about 3, 4, 5 triangles, and now I'm going to introduce a useful convention for Pythagorean triangles. Another Pythagorean triangle is 8, 15, 17. The angle in that triangle is the arc cosine of 15/17 converted to degrees. That's almost 28 degrees, but it's not quite. It's 28.07 degrees and change. I'm assigning that to the variable name A28, and in the library that I've created for this course, I've defined angles like this for Pythagorean triangles. So if you want 28 degrees to mean the angle in an 8, 15, 17 triangle, use A28, and when you use A28 as your angle, the two-component vector comes out to have precisely components 15 and 8. Similarly, I can define A53 to be the arc cosine of 3/5. That's not quite 53 degrees, but if I use A53 instead of 53 and ask for a vector of length 5, I get components that are precisely equal to 3 and 4. Now let's think about how we can do calculations involving vectors specified in terms of length and direction. This is a very standard operation in elementary physics courses. So we've got a ship. It travels 20 miles along a direction 67 degrees north of east, then 30 miles 18 degrees south of east, then goes 10 miles 25 degrees south of west. If we were doing things with pencil and paper calculation, I'd probably rig the numbers so that everything turned out to be Pythagorean triangles. But if we're using a computer, who cares? We want to figure out how far it's moved from its starting point and in what direction. Let's make an empty plot that will hold all the vectors. Got to make sure the aspect ratio is equal to 1. Our starting point is 0, 0. We'll call that O. And now I will make an element of R2 from the length of 20 and the angle of 67 degrees. I will add that vector on to my starting point O and plot the first leg of the journey. I'll make a vector out of length 30 and direction minus 18 for 18 degrees south of east. Add that on to P1 and plot my location after the second leg of the journey. I'll do exactly the same thing with the third leg of the journey. The vector sum of all those vectors is a vector from the origin to the point P3. To figure out how far I've moved from my starting point, I take the norm of that vector, and to figure out in what direction I've moved, I just take the angle between the vector and the first of the standard basis vectors. It's about 10 degrees. That concludes my discussion of these very elementary vector operations.